We're going to start chapter 6 today, and chapter 6 is about the electronic structure of atoms. Again, the electrons. And it's important to know where electrons are because after this, we're going to start talking about bonding. And when you make compounds, that's where it happens with the electrons. Not with the protons, not with the neutrons, but the electrons is where all the bonding. So the more you know about the electrons, the easier it is for you to understand when we talk about transfer electrons and so on. Okay? When we talk about electrons, they make a spectrum. Okay? The atoms, the molecules, they don't, when they run them through a machine, they get something like this. Okay? And what it is these are the energies that the electrons give off. And they're not continuous. If they're continuous, this would be like this, a solid line. Instead, you get them at certain wavelengths. Okay? So you can see the different colors and the wavelengths they give off. They actually use this characteristic of atoms and molecules to determine what they are. There's machines that can read that and tell you that, okay? So it doesn't give off a continuous spectrum like a rainbow. Instead, when you have a source of white light that goes through it, it breaks it up into parts, and then they have distinct wavelengths, and each wavelength is a special color. So each element has a unique wavelength spectrum, and then that's one of the ways they can identify what it is. Okay? We talked about the Bohr model, and the Bohr model is where you had the electron, and then you had the, you had the nucleus, sorry, you had the protons and the neutrons in the middle, and you had all the electrons going around. Well, there's like orbits for the electrons to be in, okay? And they want to be in what they call their ground state. They want to be in the lowest one available, okay? That's where they want to be, all right? If you add energy to them, they will jump up to the next level. They don't hang out in between, okay? There's levels for them, like orbits, like if you think about them as a solar system, okay? They have to be in an orbit. They don't hang out in between the orbits, okay? That, when they jump up to the higher level, that's called the excited state, okay? And each orbit has a special energy. We're not going to worry about calculating that energy. But the thing to remember, if you've ever done flame tests, okay, when you put a certain substance in the fire, it gives off a color. And the reason it gives off a color is that you gave it energy, that when you heated it and it jumped up to a higher, it was excited, it jumped up to a higher energy level. When it goes back to where it's supposed to be, it has to give off that energy. And every element gives off a certain wavelength of energy, a certain color. Okay? If you have a machine, it actually can read that color and tell you it was a wavelength of, 625, so you can tell exactly what it is. When we look at it, we go, oh, that's blue, and somebody will say, no, that's teal, no, that, it's more what they would call, it wouldn't be a quantity, it would be a quality, so it would be a qualitative, your opinion. But anyway, that happens because you're adding energy to the electron, it's jumping up a level, it doesn't want to be there, so it goes back down to its ground state, and that's where electrons want to be, in their ground state, okay? There are quantum numbers, okay? Quantum numbers explain where the electrons are, basically, okay? Every electron has what they call 4 quantum numbers. And the quantum numbers describe what they call orbitals. An orbital is a place where you find electrons. The thing about electrons is they move super, super, super fast. So you can't identify where they are, because by the time you figure out where they are, they've moved to somewhere else. They're really quick. So what they do is they say, in this area, you'll find an electron. And that's an orbital. So what an orbital is a place where you find electrons. And there's actually a maximum of 2 electrons per orbital. An orbital can have 0, 1, or 2. That's the max, okay? Well, the quantum numbers basically describe those orbitals, okay? And again, there's 4 of them, all right? Each orbital has its own place to be, and that's, again, it's a place where you're likely to find electrons, okay? And again, it's an area, okay? It's not, you can't figure out exactly where electron is because they just move too fast. By the time you figure it out, you do all your calculations, it'll be somewhere else. So they say it's in this area, and that's what an orbital is, okay? There's 3 quantum numbers that are number numbers, and then there's one more that describes which way it's spinning. So there's 4 altogether, okay? The first one is called the principal quantum number, and it's represented by the letter N. And really what it is, it's what period they're in. So like hydrogen and helium are in the first period, their principal quantum number is 1. Then you go down to lithium and boron, and those guys, their principal quantum numbers 2. So whatever row they're in. And those guys on the bottom, the actinide and the lanthanide series, if you look at their numbers, they actually go up into the periodic table. I think 72 or 73. Anyway, you'll go down to them and then they would be lifted up and they would make the periodic table super, super long. So they're just kind of taken out and put on the bottom. But there's actually 7 quantum numbers. And the quantum number tells you basically their energy level, but it comes from which row they're in. Okay, and their integers, it's from 1 to 7. Okay, and again, they correspond to the Bohr model. Again, the Bohr model said we have these energy levels and you find electrons in these energy levels. So the principal quantum number, the first quantum number, is represented N, and it's a number from 1 to 7. And it's whatever row they're in on the periodic table. Okay? They use different, here they say, okay, the value of the principal quantum number, or the angular quantum number, and this is weird to me because the angular quantum number is actually the shape of the orbital. And they gave them SPDF. They've switched it to numbers now because everybody's like, well, if it's a quantum number, why isn't it a number? Okay, so if you want to switch them, S is 0, 1, 2, 3, and you could do that, but honestly, this is still the most common thing to do. So the first angular momentum quantum number represented by L, this tells you the shape. So the second quantum number tells you the shape. SPDF, that's all they have right now. There's more than that, but that's all they've been identified. Okay, so you can see they have integers allowing them numbers, but honestly, we're gonna stick with the SPDF. If you took high school chemistry, you probably know those as well. Okay, so we don't have to switch to these numbers. Okay, the letter designates the different values of L, and it defines the shape of the orbital. So the first one tells you what level they're at. The second one tells you the shape of the orbital. So I better go through the shapes of the orbital, right? Well, the third quantum number is called the magnetic quantum number, and it tells you what axis they're on. Now, when we talk about orbitals, they're not flat. I mean, when we draw them, they're flat because we're drawing on a flat sheet of paper. That's 2-dimensional. But orbitals are actually 3-dimensional. Okay, they have a front and a back, and so if I was talking about an S orbital, which is spherical, it's a ball. It's forward, backward. It'd be shaped like a balloon if you blew it up just a little bit so that it was round. Okay, so it's on the x-axis, the y-axis, and the z-axis. So you got to remember when you're talking about the third quantum number, which is m1, it's the on whatever axis they're on. Okay, and again, they have all kinds of different numbers. The first one, the S is 0, and then, well, here I'll show you. Therefore, a given energy level can have an S orbital and 3 p orbitals and 5 d orbitals and 7 f orbitals. And again, I'll show you how that comes out about. But the magnetic quantum number is what axis they're on. So like if you're doing the p orbitals, there's 3 of them. So there'd be p sub x, p sub y, p sub z. The x would be the magnetic quantum number, or the y or the z. So when we write them out, we're not going to do all of them, but you'll see that when they're written below, and I'll show you them. That number where it tells you what axis they're on, that is the third quantum number. Okay, and here is showing them the first, because there's only 2 elements in the first one. The principal quantum, they're 1. The principal quantum number is 1, and they have an S, and that's it. When you get to the second one, you have S and you have P. When you get to the third, you have S, P, and D. When you get to the fourth, you have S, P, D, and F. Okay, so you get all these. Plus, you have all the different orbitals that can happen, because each time from when you're doing just S, it's 1. When you're doing P, there's 3. When you're doing D, there's 5. And when you're doing F, there's 7. Okay, it goes in that order. Okay, so the magnetic quantum number would be, like I said, which axis they're on. Okay, and they all have, every orbital except for S has subshells. Okay, S only has 1. P has 3. D has 5. F has 7. Okay, so to give you an idea what they look like, okay, and again, remember, an orbital is a place where you find electrons. So in this 1s orbital, and this is how it's actually mapped out. They do a density thing, but we just kind of fill it in. In this orbital, you will find 2 electrons. Then when you move up into the next energy level, it's bigger. This actually has to fit inside of this, so this has to be bigger. You'll find 2 in this one, and you'll find 2 in this one, but these actually keep building on each other. Okay, so again, the value for L, if you want to do it for the s orbital, and again, that's the S, would be 0 because there's only one different shape. Okay, they're spherical in shape, And again, this is a place where you're going to find electrons. And you notice we have all three axes here, okay? Okay, the radius of the sphere, it gets larger as you increase. So if you had 4s, it would be bigger, and 5s would be larger, and so on and so on. You go up to 7s, that's the max, okay? And again, n is the principal quantum number. It's whatever column, whatever row it's in. Okay, here's the p's, okay? Now, for p, again, this is the density one, so they make them look like kind of like a dumbbell shaped, but again, there's 2 electrons here. 2 here, 2 here, 2 here. Now, remember I said the third quantum number is whatever axis. So here we got a piece of z, a piece of x, and a piece of y. The z, the x, and the y would be your third quantum number. So like this one, if this was in the second row, would be 2, would be the first quantum number. P would be the second quantum number. Z would be the third quantum number. Okay, so I'm telling you it's in the second row. Its shape is dumbbell shape. I guess that's what they call it. It kind of looks like a symmetrical bowling pin, but we're going to call it a dumbbell, okay? And then the Z tells me what axis is on, okay? That's telling me everything. And again, there's only 2 here, there's 2 here, and there's 2 here, okay? They have 2 lobes with a node in between them, so again, they call them dumbbell, okay? Now, when you get to the d orbitals, now there's 5 of them. So again, there's 1s, there's 3p, there's 5d, there's 7f, okay? These guys start to get a little funky, you know what I mean? Now these are 4 lobes, but again, there's only 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. Okay, so they start in the third energy level because we have an S in the first, an S and a P in the second, an SPD in the third, SPDF in the fourth. So it goes on, and F is the highest they've come up with. Okay, anyway, these guys. You can see the D is fine. That's the second one. That tells you the shape. But look at these guys. This one's on the Y sub Z. This one's on the X sub Z. This one's on the X sub Y. That's their axis they're on. This is the X squared minus Y squared. And this is the DZ squared. And again, when we describe the D orbitals, we say that like they're 4 lobes. Except for this one. This one to me looks like a baby pacifier. Up and down baby pacifier. Or double baby pacifier. I don't know. But again, their shape... we just say D, and D usually associate with 4 lobes. But again, there's 2 electrons in each one of these shapes, okay? Okay, 4 of the 5D have 4 lobes. Oh, here they say a donut around a center. I still think it looks like a baby pacifier. You know what I'm saying? But anyway, this is the shape of the D orbitals. These don't start to the third level, and there's 5 of these. So if you had a full D level, you'd have 5 different orbitals. So 10 electrons can fit in there because there's 2 in each one. Now, what I did here is the book didn't even have the F. So this is all of them. Here's the S. Here's the P. Here's the D. I showed you those. The F, honestly, since I've been teaching, I only found the F probably maybe 6-7 years ago. They just identified it. And look at the funky shape here. What do you call those? 1, 2, 3, 4, 5, 6 lobes. Okay. Here we even got 2 rings, 2 baby pacifiers. But these are 6 lobe. And again, there's 2 electrons here, 2 electrons here, 2 electrons here. And look at these. F x sub squared 3 y squared. And I will never expect you to write out this stuff, you guys. That's too much. I don't have a clue what that is. But these are the shape of the F ones. And again, there's 2 electrons here, 2 here, 2. If you count these, there's 7 altogether. And those 7 each have 2 electrons in them. So if you did all of the F's for a level, there would be 14 electrons. So in this one you will find 2. In this one you would find 6. In this one you would find 10. And this one you would find 14. But these are the shapes of the orbitals. And again, the principal quantum number is 1, 2, 3, 4, 5, 6, whatever row it's in. Then you'll see S, P, D, or F. That's the second quantum number. And then this would be the third quantum number, whatever axis they're on. When we write up configurations, we're not going to write all that out because that's a lot of work, believe me. So we just go with, you know, the S, the P, the D, or the F. Okay, and I'll show you how to do those next one, I think. Okay, here's hydrogen. Again, hydrogen only has 1 orbital. It's a really small one. It actually only has 1 electron, so it has 1 s orbital with 1 electron in it, and that's it. Okay. Those orbitals, they can call them degenerate, but again, we're not going to spend a lot of time talking about that. Let's see. I'm trying to see. We'll quit right here because we're just about out of time. So this is where we'll pick up next time we take notes.